Hello everybody, it's Mr. Gustin back in the physics classroom today. Second video today, wearing the same shirt. I'm going to walk you through an example problem of conservation of angular momentum. Okay, so first things first, let's walk through the problem. I got a little kid, and this little kid is running. This is kind of a bird's eye view. This little child is running at a merry-go-round on the playground, jumps, and as they jump, they land on the merry-go-round, and that merry-go-round starts to spin. And your question is, what is the final velocity of the system, of the merry-go-round, after this child does this, right? Big question. What is the final velocity? They jump, they land, they start to spin. You can imagine doing this, and if you haven't done this yet, go find a local merry-go-round, give it a shot. Gustin didn't tell you to do it, but it's fun. Give it a try, okay? So I'm going to actually look at both the child and the merry-go-round together because I want to make sure that there are no outside forces on the merry-go-round. I don't know what kind of force this child is going to apply to the merry-go-round, so I just want to examine the child. Okay, so because I know the child and the merry-go-round are in the system and there are no outside forces, I can say the momentum before this collision and after this collision is conserved. It's the collision because I have one object jumping onto the other. This is a collision. Momentum is conserved. So I need to think about where the momentum is stored initially. And so initially there's momentum in the kid. And then afterward there's momentum in the kid. And there's momentum in the merry-go-round, which I'm going to abbreviate MGR. If I think about these equations, now I got I of the kid times omega of the kid is equal to I of the kid times the speed of the kid final plus I of the merry-go-round times final of the merry-go-round. A couple things I can do here. I know that both of these final angular speeds are the same because the kid jumps on the merry-go-round and they move together. So this, I'm going to rewrite this as I kid plus I of the merry-go-round times just the final velocity. Now this is equal to I of the kid times the initial velocity this kid has. Now here's the weird thing. We break this down and they say, well, Gustin, hang on. This kid is moving literally on a line. There's no angular velocity of this kid. They're rotating, or they're moving straight on a line, and then they jump. And you're telling me that this kid moving in a straight line has angular momentum? And I'm going to say yes, they do. Because this kid, no matter what, as this kid runs, the only part that we're really concerned about is the kid right as they are in the air. As they are in the air, like, right before they hit the merry-go-round. That kid definitely, about this axis of rotation, has a radius and has a tangential speed. And when I take that tangential speed and that radius, I can figure out what their angular velocity would be at that moment. I can figure this out, and that should make sense, right? There's a tangential velocity, there's a radius about a specific axis of rotation. I know exactly what that angular momentum is of that kid. Even though they're moving tangent, they're just a point at the edge of a circle. Got it. So now let's look. What kind of shape is this kid? I don't have I for the kid, but the kid's a point mass. So the kid's I value is going to be mass times r squared. The initial angular velocity I don't know, but I do know their linear velocity, and so don't forget about our bridge equations, right? This angular velocity is v over r. So let's just go ahead and say it's v over r. That's the kid. This equals I of the kid, which is just going to be mr squared for the kid, plus the I for the merry-go-round, which was told to me is 500 kilogram meters squared. So 500 kilogram meters squared times the final velocity, and that's what I'm looking for. Okay? So I can do some algebra, I guess, bang, bang. mrv of the kid is the initial momentum. mr squared of the kid after they jump on the merry-go-round, kilogram meters squared, this whole thing. Find me final angular velocity. I'll start plugging some numbers in, and when I do that, I'll use the red marker so we can see really clearly what I'm doing. But the mass of the kid, 40 kilograms. Got it. The radius of the kid, they land right at the edge, so they jump at a distance of 2.5 meters relative to the axis of rotation. The initial speed of the kid was 3 meters per second tangentially. This is equal to the mass of the kid, 40 kilograms, times the distance they jump at, 2.5 meters squared, plus 500 kilogram meters squared. And I'm looking for final velocity. Let's go ahead and solve this problem, figure out what the final velocity should be. Should it be more or less? Well, 3 meters per second isn't really something I can compare to. I should be comparing it to its initial angular velocity. And the initial angular velocity is 3 over 2.5. Call it, right, a little more than 1. This value should be definitely less than 1. This kid should be moving slower than he was before because he jumped onto the merry-go-round. Let's do it. 40 times 2.5 times 3 is this. Divided by 40 times 2.5 squared plus 500. Close that parenthesis. I end up with, and tell me if I'm wrong in the comments, but I end up with final speed is 0.4 radians per second. This is what I end up with. That makes sense. It should be less than the initial velocity, angular velocity of this kid, because I've just increased the mass of this system. I've increased the rotational inertia. So this is an example of how two things. One, a linear object does have angular momentum about a point. Two, how to solve a mathematics problem when angular momentum is conserved, when there's no outside torques on my system, and I was able to treat this system as the kid and merry-go-round. Therefore, there were no outside forces. Had I just looked at the merry-go-round alone, there is an outside torque. If I had looked at just the kid alone, there is an outside torque. Put them both in the same system, no outside torques. Initial angular momentum equals final angular momentum. I'm able to solve this problem mathematically. If you've got questions, drop it in the comments, send me an email, or as always, ask me in class. Until next time, see ya!